Hi, my name is Leghorn, and I'm going to be doing a tutoring video about quantum numbers. So, we have 3 learning objectives today. First, what is a quantum number? Then, what do each quantum number equal in an orbital? And then finally, why and what are the restrictions of each quantum number? So first we're going to do what is a quantum number. And quantum number are a set of 4 numbers, n, l, m sub l, and m sub s. And these numbers indicate the alignment of the unique quantum position of an atom, electron around an atom. So this indicates its energy, location, and orientation in space. So going from there, we're going to get an example of a quantum number. So we'll do 5, 2, 1, 1/2. So taking this and changing it directly into an orbital, we have 5 t So this is it transferred directly into an orbital. And let's explain what each of these numbers correlate to. So we're starting with n. N is directly changed from its number in the quantum number into the orbital. So here you can see 5 to 5. But what changes is the L. L is a 2, but here it becomes a D. And so this is because each number for L in the quantum numbers changes to a letter. So L. So let's just go over the 0, 1, and 2. 0 equals S, 1 equals P, and 2 equals D. So here, because it's 2, it becomes D. Now, M sub L is 1, and so we fill up to the 1 orbital, and then M sub S is the indication of the orientation of the electron around the atom. So right now, because it's positive 1/2, it is going up. So that's how we transfer the quantum number into an orbital. Finally, why and what are the restrictions to a quantum number? So we're starting with n. N can only be a whole number greater than 0. Next, L can be a whole number greater than or equal to 0, but also it has to be less than or equal to n minus 1. So that's the bounds for L. Next, M sub L always has to be between negative L and positive L. So here, it's 1, so that's between negative 2 and positive 2. And finally, M sub S can only be negative 1/2 or positive 1/2. So you can see here, all of this falls into the bounds of what a quantum number can be. So let's get an example of a quantum number and a couple quantum numbers and see if you can identify which one is false. So we'll start with 3, 2, 0, and 1/2. 4, 0, 0, negative 1/2. 3, 1, negative 1, 1, and then 1, 1, 0, 1/2. So take a second to pause the video, and when you're ready, restart it and we can figure this out together. So let's go through each of these. And the way I like to do this is to start by each letter. So first we start with the n numbers. And we know that n has to be greater than 0 in a whole number. And you can see each of these are greater than 0 and they're a whole number, so n is fine. Then L has to be greater than or equal to 0, and it has to be less than or equal to n minus 1. You can see here, each of them, some of them are 0, but each of them are less than or equal to, wow, n minus 1. Except for this one. So we have one error right here, because n is equal to 1, so this would have to be 0 and only 0. And since it's 1, this is incorrect. This cannot be a quantum number. Then we can keep going because there is one more error in here. And so we're going to m sub L, and m sub L has to be between negative L or positive L. And so here is always between negative L or positive L in these remaining examples, including this one, but that one's already crossed out. So this isn't our issue. Then we can see here, this is honestly the easiest category because it can only be two numbers, negative 1/2 or positive 1/2. And you can see the big glaring issue here is a whole number 1. So this one is also can't be a quantum number. So let's go back over everything we went over. So first of all, what is a quantum number? And we can see the 4 of them here. And remember that they indicate the electron's orientation around an atom. Then what quantum number equal in orbitals? We took an orbital and transferred it into a quantum number, and it went through each step to show which of these correspond to each spot in the orbital. And then finally we went over what are the bounds and why they are there. Alright, so I hope this helped, and thank you.